All right, hey students, Mr. Cabley again. Um, I just wanted to start off with the answer to yesterday's questions, those 5 questions on the back of yesterday's paper. So if you don't already have that out, go ahead and grab that out, whoever's playing the video can pause it so that you can get those questions out and check these answers. Sorry about number 5. Okay, moving on. Today, we're going to talk about specific heat capacity of different substances, and this may be your first time ever hearing of specific heat capacity of different substances, so congratulations. We're going to start off by watching an experiment. What you're going to see in the experiment is you're going to see 2 beakers, one with water and one with isopropyl alcohol. They're going to be heated. Actually, this says on equal settings on identical beakers. You're going to see that they're heated on the same heater in the same type of beaker. So basically what that means is that they're going to get the same amount of heat. Remember, heat is measured in joules. So the 2 beakers are each going to get the same amount of heat, and we're going to just observe the results of that. So here we go. You see the 2 different beakers. They're going to get temperature probes added to them. And they're going to get placed onto the heater. So now we see in the bottom left corner the temperatures of each one. They started off at the same 22.5 degrees Celsius. And now look, the one on the right, which is the alcohol, is measured in red. Notice that its temperature is already higher than the temperature of the blue one, which is the water one, the one on the left. And now the experimenter has sped up time, so you see the time traveling really fast. Over time, this is the temperature of the red, which is the alcohol. Notice how the red temperature, the alcohol temperature, is going up much, much faster than the blue temperature, which is the water temperature. So we see the alcohol's temperature already almost to 40 degrees Celsius, and the water temperature is still 30, 32 degrees Celsius, 33 degrees Celsius. So clearly, the alcohol is increasing in temperature faster than the water is increasing in temperature. So I'm just going to go ahead and pause it right there. We can observe this result. This is the result I want us to observe. That after 50 seconds, the temperature of the alcohol has increased a lot, and the temperature of the water has also increased, but not by as much. Even though they're on the same type of beaker, on the same heater, which means that they are receiving... Hold on, baby's crying. There you go. They're receiving the same amount of heat, but the alcohol has increased its temperature more. So what does that mean? First of all, that's another demonstration that heat and temperature are not the same thing. But more importantly, it really demonstrates our purpose of today, which is specific heat capacity. So, specific heat capacity is the number of joules. Whoops. Specific heat capacity is the number of joules of energy that it takes to raise the temperature of 1 gram of a substance by 1 degree Celsius. So go ahead and copy that definition there into your notes. The definition of specific heat capacity. And let's see. Ready to move on? All right, I wanted to point out the chart. This chart here appears on your paper. It shows the specific heat capacity of different substances. One of them is isopropyl alcohol, and one of them is water. Notice that the isopropyl alcohol has a lower specific heat capacity, meaning it takes less heat to raise its temperature. So the isopropyl alcohol has a specific heat capacity of 2.6, which is lower than water's, which is 4.19. This means it takes less needed to raise the temperature for the alcohol. And the water it needs more heat to raise its temperature. Does that explain the results of the observation that we just did? Yes, because the two substances, the water and the alcohol, were receiving the same amount of heat, but the alcohol's temperature increased more because it doesn't need as much heat to raise its temperature. So that's why it heated up faster. Does that make sense? I hope it does. All right, so what I want you guys to do is use this information to answer questions 2, 3, and 4. So whoever's playing the video would please pause the video so you can answer those questions. All right, moving on. There's a formula. This is the formula. Q equals M Cp delta T, where Q is the heat added to or removed from a system, that's measured in joules. M is the mass of the substance, measured in grams. Cp is the specific heat capacity, that's measured in joules per gram degree C. And delta T is change in temperature. Remember, delta is always T final minus T original. It's always final minus original. And that can be measured in Celsius or Kelvin. So I'll give you a second to get all this down. All right, so first example. A cup with 200 grams of water, and by the way, this example also appears on your paper. A cup with 200 grams of water is raised from 30 degrees Celsius to 55 degrees Celsius. Okay, so that gives us the original and final temperature. So delta T is equal to final minus original, so 55 minus 30. 55 minus 30, that's 25 degrees Celsius. 200 grams of water. Okay, so that's mass equals 200 grams. It's water, so we know that the Cp of water is 4.19. So how much heat was added? So it wants to know what is our Q value. So Q equals mCp delta T. So Q equals M, which is 200, times Cp, which is 4.19, times delta T, which is 25. And I hope you're doing this along with me. So then Q equals all those numbers multiplied to each other. I get out my calculator here. So 200 grams times 4.19 times 25, which was the delta T. That gives 20,950. So 20,950 joules, because it's a heat. All right, so that's the answer to the first example. Moving on. Example 2. A cup with 500 grams of vegetable oil. So that's mass is 500 grams. Oh, we know the specific heat of vegetable oil. It's in the chart. The specific heat of vegetable oil is 1.67. It's cooled. Oh, that means its temperature is going to go down. Delta T will be negative by removing 5,010 joules of heat. So Q is negative 5,010 joules. If the original temperature was 90 degrees, what's the final temperature? Okay, so T original is 90 degrees Celsius. It wants to know what is T final. Okay. All right, so what do we need to do? Well, we need to use Q equals mCp delta T. We're going to find delta T. We're going to solve it for delta T. And then once we know delta T, we'll do delta T equals T final minus T original to solve for T final. So Q is negative 5,010. Mass is 500. CP is 1.67 times delta T. All right, so then we'll just divide by these things. We'll just divide them under and we'll get what delta T is equal to. So 5,010 divided by, open parentheses, 500 times 1.67, close parentheses, 6. Whoops, did you see that? 6 is the answer. So 6 equals, oh wait, and it should be negative 6. Negative 6 equals delta T. Why negative? Because I forgot to do the negative and 5,010. So negative 6 equals delta T. So then negative 6 equals T final minus T original, which is 90. So I'll add 90 to both sides. And I'll get that T final is negative 6 plus 90. So T final is equal to, what's negative 6 plus 90? 84 degrees Celsius. So what was its final temperature? Its final temperature was 84 degrees Celsius. All right, so I hope that that was good enough for examples for you guys. I would like for y'all to my computer's frozen. Why is my computer frozen? Anyways, I would like for y'all to complete the practice problems on the back there. Just so you know, there's going to be a quiz tomorrow, and that quiz is going to cover things from yesterday and the things from today. So you are going to be responsible for both of those things. All right.